days ago. I think we might have managed to actually do that in the time. So let me introduce with that slide here to give people an overview, so especially to the students. The current state of the art of numerical relativity matter simulations is basically you fully solve the Einstein equations in various formulations. So you have finite difference codes, you have pseudo-spectral codes, and there's also a different formulation which is called the generalized harmonic formulation. You have GIMHD, which is usually done using high-resolution shock capturing methods for hyperbolic conservation laws. And there's either constraint transport, constraint damping, or the vector potential evolution to maintain the solenoidal constraint during these evolutions. And again, there's various groups in the world that have working codes here. I apologize, every time I put up this slide, I'm afraid that somebody's in the audience who's not mentioned here, so if you are, I'll happily buy you a beer as an apology. The microphysics is basically two parts, so you have to close the evolution equations by specifying an equation of state, which is basically the relation of how pressure and temperature are related. And so by now people are able to use realistic equations of state beyond polytropes and ideal gases that are temperature and constitution dependent. And finally, there's neutrino treatment. So there are leakage schemes which basically remove energy from the system by emitting in neutrinos. And there's also the truncated moment formalism, which basically allows for heating. So the neutrinos can remove energy, but then they heat the fluid in other parts as well, because we're dealing with very high densities here. So the mean free path of the neutrinos and the cross-section of the neutrino matter interactions are quite high. So it's not like the Earth where the neutrinos pass through basically undetected. You have to really count them in the systems that we're playing. As far as I know, the majority of codes that do full numerical relativity simulations, so we solve the space-time together with the fluid equations, use Cartesian grids to do the fluid evolution. And the thing with Cartesian grids is, given that we have very wide-ranging time and length scales, so here's a mesh-refining grid structure of a sample black hole torus simulation I did while I was a PhD student at the University of Valencia. So you have a small black hole here, which is in size very small compared to the torus, and you need high enough resolution at the black hole to resolve the space-time that via finite differencing. But you also need high resolution in the hydro, so the grid has to extend very far away, and Cartesian coordinates are just due to the fact that they over-resolve the angles as you go outwards, so the number of points grows to the cube. You basically cannot have that really high resolution all the way in the domain. So what you need to do is you need to essentially use mesh refinement, where you basically place a very fine grid over the black hole, and then as you go out, you basically have less and less refined grids. And this causes energy and linear momentum loss at mesh refinement boundaries, although that can be cured with a technique called refluxing, where you specifically account for the fact that you need to redo the fluxes, so the flow through the boundary can be corrected in order to have energy and linear momentum conservative codes. But even with the refluxing, the space-time is noisy, so you have basically waves traveling through, so the ripples in space-time, as you've often heard, they travel through, and at each mesh refinement boundary, they're basically partially reflected, and that noise is never really allowed to leave the grid. So if you're interested in high accuracy gravitational waves, for instance, from these systems, that's going to be a problem because the noise is very high in high order multiples. And most importantly for accretion physics, so that's something that in the accretion disk community, people have been using other types of coordinate systems for decades now, because Cartesian meshes do not conserve angular momentum. That's ultimately due to the fact that if you have an azimuthal flow, in the majority of the grid cells, your flow is going to be misaligned with the cell faces, so you always have diffusion, then you lose information and basically lose angular momentum. And as we know from accretion physics, losing angular momentum essentially means triggering accretion, because you need to transport angular momentum outwards in order to accrete matter into the central object. So the majority of these codes are basically overestimating the accretion rates, because they remove angular momentum from the fluid and therefore triggering faster accretion. So is there a coordinate system that has these features, or, well, basically has the opposite of what the problems that I talked about? And there is, those are spherical coordinates. So they have all the attractive features that we're missing in Cartesian coordinates. So they have a low memory footprint and no mesh refinement is necessary, which is basically due to the fact that as you go out in R, you only grow the number of points by the number of radial points because the angular number of points stays fixed. They reflect the underlying approximate symmetries of many astrophysical scenarios. So, of course, black holes are axisymmetric or spherical objects as long as they're unperturbed. Accretion flows are azimuthal, so in spherical coordinates you have the azimuthal flow actually is always perpendicular to the cell faces in the phi direction. And then signal stars, or neutron stars, pulsars, for cork-like supernovae also are approximately spherical. And most importantly, so spherical coordinates conserve angular momentum in finite volume hydrodynamic modes. So what we actually did, we built upon the computational infrastructure that Roland gave an overview on in the Einstein Toolkit and enabled the use of spherical coordinates. So I'm going to go through in a very, very high level description of what we actually did. If anyone is interested in the boring details, before though, I tried to sell you a broken motor cycle. So obviously I have to mention the caveats here. So there's no free lunch, obviously, because spherical coordinates are much more complicated to deal with numerically than Cartesian coordinates, and that is of course due to the fact that a single coordinate chart in spherical coordinates is not sufficient to cover all space due to the coordinate singularities at the origin and the z-axis. So the determinant goes to 0, which causes also the problems because volumes become 0, and then the coordinate vectors in spherical coordinates become multi-valued, so you have all sorts of problems. If you can get around that, there's another problem you have to then think about. So there's a severe time step limitations due to the fact that the cell volumes in spherical coordinates are not constant throughout space. So going from the equator up to the axis, you basically, if you have the same number of points in phi, the radius of your the cylindrical radius becomes smaller and smaller, but you still have the same number of points. So the distance between the cell sizes becomes smaller and smaller, and if you do hyperbolic PDEs, the distance between the cell points basically limits how far in time you can step ahead in a single step. So in spherical coordinates, you have to use very, very small time steps. Very small time steps. Okay. And finally, vector and tensor components of coordinate vectors contain terms that diverge near the origin and axis. So you basically have 1 over r and 1 over r sine theta, and in the worst part of the metric, you have terms that diverge as 1 over r squared sine squared theta. So you have to be really careful. I don't have time to go through the details, and I left this out because Thomas Baumgartner, who's one of the developers of the formalism of what we actually use, is going to talk in much detail about this in his talk. So I'm just going to say, trust me that there's a magical way to get around these problems with the diverging terms, and let's just think about how we implemented it then. And then Thomas in his talk will talk about what that way actually is. So the way we implemented this is that noticing that if you remove the z-axis from the grid, you can actually map spherical coordinates to topologically Cartesian coordinates in a one-to-one fashion. Which means if you set up a grid in a way that where r goes from the innermost radial point outwards to your maximum radius, and theta goes from delta theta half to pi minus delta half, and phi, because it's a perfectly valid coordinate, nothing is happening here, it goes from 0 to 2 pi minus d phi. If you set up such a grid, then you can unroll that into a cube of numerical coordinates that are Cartesian. And what you then need to do, for finite differencing, you need ghost zones, and those are provided by internal parity boundary conditions. And what you do for those, basically, if you picture a globe that you had at home when you started learning about the world, you go through radial rays through the origin, and you know that on the other side of the radial ray that goes through the origin, there is a live point because you have other grid points there. And you basically fill the ghost zones that you need to find a difference in the radial direction by the information of the grid at that point, and then you need to multiply it with appropriate parity factors because due to the fact that the coordinate vectors in spherical coordinates change sign as you go around the globe. And you do the same thing in the theta direction where you follow meridians across the north and south pole. And again apply appropriate parity solutions. We did that. Here's a schematic drawing of what that actually looks like. So we used the slab thorn, which provides you with MPI parallelized 3D subarray manipulation and broadcast. And we basically take live points in the grid, transform the slabs, and broadcast them into the ghost zones. and then you need to multiply vector and tensor components with appropriate parities. And those are the parities for densitized or rescaled vector components. If the coordinate vector components have different parities because it depends on if you have rescaled vectors or not. So you basically take data from here, you need to invert, that's the origin, so you go from r goes to minus r, and theta goes to pi minus theta, and then in phi you need to rotate by pi, and that is basically being done in that transfer of data into the slab. And once that was written, we basically had our boundary conditions, so the only real physical boundary conditions in the spherical grid is the outer radial boundary. All the other boundary conditions are internal and cannot be used by that thought. And once we've written those boundary conditions, they're generic in a way that they can be applied to any grid function that you have in the grid. So you can use those boundary conditions for your space-time evolution and the higher. So I'm going to go through a couple of slides. First, here's a result for a run of a single bow New York black hole, which is a spinning black hole that is conformally flat. So it is a curved black hole that basically has a non-zero gravitational wave constant inside, because we know that it's not conformally flat. So what you're going to see is there's going to be that's psi4, the way it's getting. So you basically see this beautiful radiation of psi4 leaving the black hole and then reaches the outer boundary, so there's some reflections there because the boundary conditions are not well posed, so some comes back in. But if you've seen similar videos like that in Cartesian coordinates, you don't get that shape. There's reflections at every measurement point and boundary where as the wave travels out, it is partially reflected and then it becomes really, really noisy. So in order to check the quality, we do a multipole expansion of the signal at a finite radius. And here I'm plotting the higher order multipole components with SphericalBSSN. So that's the absolute value of the wave scale up psi4, which at infinity is the outgoing part of the gravitational radiation. And on the left side are the even order modes for m equals 0, so different L and m equals 0 modes. And on the right are the odd modes in order to make the figures less crowded. So you see you have a peak amplitude here, and then you have a very nice monochromatic exponential decay in the L2 mode. But as you get to higher modes, we started observing those beatings, which we were concerned about because the ring down of the signal should be monochromatic in all the modes. So we were not quite sure what was going on first, but the solution to the puzzle came, explaining that beating, is that we were seeing spheroidal spherical harmonic mixing. So the frequencies and the damp rates of the ring down are basically described in spheroidal harmonics, which are spin dependent. And it is known that the spheroidal and spherical harmonics mix L modes of equal m. So what we're basically seeing is that we extracted the signal in spherical harmonics, and therefore the extracted signal showed that mixing of the different modes, which introduces that beating. And we got the ring down frequencies and damping coefficients from Emanuele Televerti on his webpage. You can go there and download them. And if you actually fit the mixing to the data, you see that you should have extracted those in spherical harmonics. So we saw very clean ring down to curve, very high order, and that was quite nice. That wasn't possible to do with the Cartesian simulations that we performed because the higher order modes get completely not destroyed, but they lose the information due to the reflections of the magnetic particles. All right, but I mean, nobody wants to write a 3D code just to do black holes, especially not single black holes. So we wanted to do GMHD in spherical coordinates. So the microcode is production ready. We actually added CCZ4 for matter evolutions as well. And we've implemented and tested general relativistic magnetohydrodynamics in spherical coordinates. And the main idea based is on Montero et al. So the formalism that Thomas is going to talk about on Wednesday. He and collaborators also did that for Hydra, just using a reference metric approach with a 3+1 Valencia formulation of GMHD. So they presented results for Hydra, and then I extended it to MHD as well. What you basically get is you rewrite the equations with a reference metric, and you have the appearance of geometric source terms due to finite differences with respect to the spherical reference metric. And here's the overview of what we've done. So we implemented GMHD reference metric formalism in GeoHydra, which is one of the two publicly available GMHD codes already in the toolkit. We used the cell-centered vector potential evolution in the generalized Lorentz gauge, which is also done in the GMHD code and as well in WSGI MHD. Okay. And all variables are properly rescaled, which basically means that we evolve vector components in the orthonormal basis with respect to the spherical reference metric. And once you do that, you have to replace partial derivatives with covariant derivatives of the background metric. And the way we've written this is that it incurs minimal changes to GeoHydro. So only in those geometric source terms, and those are NURBY generated, just as the right-hand sides are NURBY generated as well for the space-time evolution. And we pass the rescaled ADM-based metric to GeoHydro. So because all the components are rescaled, you have to pass the physical metric in the orthonormal basis with respect to the spherical background as well. And because the code is logically Cartesian in the way that we set it up, reconstruction and Riemann solvers and all the other infrastructure that is already present in GeoHydro can just be used out of the box, which was my lazy man's attempt of getting there as fast as possible. So I didn't want to reinvent the wheel and write everything from scratch, so we wanted to use as much as possible of already tested code. All right, so let's get to some cool results with code. So here's one test, which is called the spherical relativistic shock reflection. So yeah, in 3D, you set up a uniform fluid that has an inflow velocity everywhere, which means that as it reaches the origin, it cannot go anywhere. So you form a hard reflecting ball. And this is the solution of the density in R at a time of 1.7. So here you see that this wall has formed, but there's a steep gradient here. And outside the solution follows pretty much the analytic solution, which is the analytic solution in the cold case. That wasn't completely cold. There was a bit of it added some temperature there, but it looked fairly well. So that was Hydra only, and then we are going to a more demanding test. So what I set up here, two things. So you're going to see that wedge here in all the videos and the wedge being absent downstairs. I'm not sure if that's the way carpet outputs the data, if there's a visit artifact. So there's no real wedge here anyways. So given that we removed the z-axis, all our points are actually cell centers. So the entire grid is basically a cell-centered grid. So the point that visits plots over here is the cell center of the first point. So the face actually lives on the axis. So there shouldn't be that artifact. I have to see what is going on. But in case anybody asks me, I pre-answered your question. So what we did here is basically you have a spherical ball here, which is a higher density and pressure than the ambient medium. There's an exponential matching region, because otherwise, in the Commissaro paper, where that was being done first for the cylindrical explosion, I think they say if you don't exponentially match, the shock is just too extreme. So we followed that and set up that matching region. And the entire domain is threaded by a magnetic field that is aligned with the z-axis. So that means that the magnetic field doesn't really conform to the symmetries of the coordinates. And then we're going to see what just happens. So the explosion will proceed, and will basically start growing out. So plotting the pressure here, and you see that we form this shock front here, which is, so the explosion happens in an asymmetric fashion. So it's still axis symmetric, but you have to compress the magnetic field as you travel out in that direction. And over here, you can basically, the shock will escape more freely. And the region in the middle is spherically symmetric because you basically removed all the magnetic energy from the center. So by the time the rarefaction wave comes going back in, the fluid is now doesn't have to go through the magnetic field anymore. So basically, the solution becomes spherically symmetric again. And now you would say, so I showed this to Scott over there, and of course he asked me, well, that's nice, but can you do a harder test? So the next thing I'm going to show you, well, first I'm going to show you some field lines. So the field lines are just color-coded white, so you can see them, but if I would have overlaid the magnetic pressure in the middle, then it would have, the magnetic field would have been almost completely removed. So you went from not being dominated by magnetic pressure anymore. But you basically see how the field lines get compressed into that region here. And so Scott asked me about what would happen if the magnetic field is initially tilted with respect to the axis. So now it becomes becomes a full 3D problem because the direction that is being picked out by the shock, so the field line that threads the sphere and where the problem is axisymmetric about after the explosion proceeds is now misaligned with the grid, so you need to have full 3D resolution. So that is that was 30 points in theta and 60 points in phi. And we're going to see if the code is able to perform well in that problem. So you see there's some things happening here near the axis, but basically the shock explodes, and you can clearly see that it picks out the line. So the symmetry line is now at 45 degrees. And then there's some artifacts here, and then the shock seems to stall earlier than the other case. But you could do higher resolution, I guess, and get better results. But that's a fairly complicated problem for a code, because now you kind of broken symmetries and you don't. You wouldn't have a Cartesian grid like that, a Cartesian field like that in any real simulation. And here I'm basically plotting the aligned case, it's a Lorentz factor, and the misaligned case. So the Lorentz factor as well shows picking up the axis of the field, and below again the pressure for both of the cases. So I would say that worked fairly well, and I guess with high resolution you get even better results. And then I did a test that is even more difficult. So at least the fluid was exploding in a way that still reflected the symmetries of the grid, whilst the magnetic field wasn't. And now we're going to have the fluid explode in a way that is really, has nothing to do with the symmetry. So remember, in spherical coordinates, the field lines go up like that. So the whole point that you line the flows with the line, with the faces, is now broken. So same thing with a magnetic field, this time not tilted, but aligned with the z-axis, and we place the sphere off center and see if we can actually pass the shock through the origin of the axis. So it explodes here. There's some artifacts that start developing, but overall it seems to maintain the same shape. It goes on. Then once the rarefaction wave actually comes back and evacuates the region, there's something going on here that I have to talk with the geohydro people about. If you see the minimum density or the minimum pressure drops well below the atmosphere value, which shouldn't happen. I'm not sure how it's able to do that. But at least the shock kind of went through the origin of the axis. And the main feature here is that, of course, in spherical coordinates, radial fluxes need to be converted into angular fluxes in order to flow around the sphere of the origin and flow around the axis, right? So you need very high resolution. So I would assume that if I double the resolution here, which is then going to be very slow due to the time step, then you get a better result than you can. But we managed to pass the shock wave and compression of the magnetic field through the origin and the axis. So that's a very, very difficult test of the code that the code has done. Here's the same thing, so the initial data and then two slices. One is the vertical slide at the end of 4, and then here in the z direction. So you see that the origin causes some sort of like a little bow wave where you need to go around the origin. And I think that effect is going to be reduced with higher resolution. All right. Some other results is a couple of plots from TUV collapse and hydro only. So we basically you start with the TUV, and then you do whatever your favorite method is to induce collapse. So you can reduce the pressure everywhere a bit, or you can change the K constant, which is what I did. So there's like a 2% drop in pressure overall in the star, and then it's not stable anymore, it collapses, and that's how the collapse proceeds. So that's the central density over the initial central density. So you see there's a steep peak here, and then you basically form a black hole. And the star should be swallowed in its entirety, so the ADM mass of the system has to be equal to the irreducible mass, and that's what we show here in those plots. And calculate the ADM mass as a surface integral, and that is basically two different simulations where we put the outer boundary further away to get less noise there. So that seems to have worked well. And we implement FCCZ4 in spherical coordinates, and everything seemed to work fine for the neutron star. Next, I'm going to show you a rotating neutron star with an initial colloidal magnetic field. So here's the initial data, that's the density. And here's the density after 3000 M, which is a bit more than 100,000 timescales of the star. And you see that the star, has hardly done anything and hasn't been deformed or anything, and especially the atmosphere layer seems to look very, very clean. So downstairs I'm plotting the same again, and here the maximum value is 1 times 10 to the minus 9. So you see the star has lost hardly anything to the atmosphere. So that's the stable model BU2, which we generated with RNSID, and the colloidal magnetic field. And for those simulations, I used the positivity preserving limiter that David Radic has implemented in
So the color here is density?
Yes.
And magnetic field is confined inside.
Confined inside. So the positivity preserving limiter was really important to get that really nice interface working of the stellar surface and the atmosphere. And as a last test, which is actually a bit outdated, so initially I implemented flux CD, which is a cell-centered constraint transport. And that is mathematically equivalent to evolving the vector potential in the algebraic gauge, which is known to have a zero-speed mode, and therefore I was seeing problems at the origin. And then I went and implemented the cell-centered vector potential in the Lorentz gauge, and that seems to have made things much better. So that is the older version, which didn't survive as long, but that is a full 3D simulation with the same model as before, BU2, which is mildly rotating. And the rotation axis of the star is initially aligned with the x-axis. So the star will rotate through the axis, the coordinate axis, and would therefore drag the magnetic field with it through the axis. That was to test whether we could actually have something that is really not like a toy model test, but something physical where we could see that we can have full 3D simulations. So you can see that those are the magnetic field lines during the evolution. So you see that the magnetic field is passed around as the star basically rotates through the axis and drags the field with it.
So the magnetic fields are fixed. So the direction of the dipole that generates the magnetic fields
was initially aligned with the polar axis,
right.
But then the evolution is.
But basically, the magnetic fields are not changing, right? So if the rotation of the star is the rotation of the fluid, which is ceding the magnetic fields, the magnetic field line should be distorted as well, right?
Yes. You drag the field with you as the fluid rotates, right? And then there's some
I'm just surprised you don't see any surprising disruption in the magnetic field lines. You don't see any entanglement with the magnetic sphere of the star. And we don't know.
This is not the DNS post-merger scenario, yes. So this is highly symmetric.
I see, but it's still.
So magnetic field is still confined just inside, right?
yes,
Okay, so
and it's a weak field, so it should be just rotate with classically. You still get some deviation from so the field doesn't remain colloidal, right? Because you actually mix.
And you make out something like a looping holes.
Yes, exactly. So you start having some toroidal components.
And what is the rotation? What is the rotation speed of the star?
The axis ratio is 0.9, so that
It's slow rotation.
it's very slowly rotating.
Okay.
But that was because it was in full 3D. So the higher the rotation rate, the more angular resolution you needed. Then that would have been slower. So I'm going to redo that test now that I've implemented the vector potential practitioner that has solved the problems with that.
And you can do
Fluxity.
arbitrary directions with the spin and the magnetic field.
You can do whatever you want, yes, because it's both 3D. So sorry for running 2 minutes over. So as a summary, Spherical NR, which is the framework, enables the use of spherical coordinates in the Einstein Toolkit using a spherical reference metric approach for both the space-time, and here we have the BSSN and CCZ4 formulations, and GMHD and the Valencia formulation. We've adapted GHydron to work with spherical coordinates and implemented GMHD via cell-centered vector potential evolution in the generalized Lorentz gauge. And the vector components of the vector potential and all the other vector components are evolved on an orthonormal basis with respect to the spherical background metric. And once the last glitches with the atmosphere, which is always the most horrible thing for everyone, are sorted out, there will be a code paper